In this presentation, I'm going to explain Bayes' theorem, the rationale behind the theorem, some of its applications, and some of its strengths as compared to other ways that someone might reason about new pieces of evidence. I'm going to first show how Bayes' theorem follows directly from more fundamental statements about the probability of conjunctions and about conditional probabilities. And then I'll go on to talk about its strengths when it's applied to understanding the relationship between hypothesis and evidence in support of that hypothesis. I'll also say a few introductory words about Bayesian epistemology, though I won't go into a great deal of depth about it. So Bayes' theorem was first formulated by Thomas Bayes, an 18th century statistician and minister, who was best known for this particular theorem. The theorem wasn't actually presented by him during his lifetime, but was presented to the scholarly community a couple of years after his death by a friend of his. It's important to distinguish Bayes' theorem from Bayesian epistemology or a Bayesian approach to statistics or anything else. That's because Bayes' theorem is something that follows with necessity from certain definitions of conjunction and conditional probability. And because it's a theorem that follows from the basic axioms or definitions of probability, it means that it's something that is accepted and must be accepted by every approach that someone might take to epistemology or statistics. So frequentist statistics or non-Bayesian epistemologists sort of don't have a choice about accepting Bayes' theorem. When it comes to a Bayesian approach to epistemology, though, some of the key things that distinguish this as an epistemology are things that don't follow with necessity from the basic axioms and definitions of probability theory. So I'll come back to this distinction later in the presentation. There are a few terms I want to introduce right now to set us up to talking about the basics of Bayes' theorem and Bayesian epistemology. And one is that the unconditional probability of an event is referred to in this context as a prior probability, and the conditional probability of that same thing given something else is referred to as the posterior probability. We'll see some good reasons momentarily why the terms prior and posterior are pretty good labels for these conditional and unconditional probabilities when you look at how Bayesians actually want to think about the process of updating your beliefs in light of new evidence, a process they call conditionalization. One other term we need to put on the table is likelihood. So likelihood in the Bayesian context, in the context of using Bayes' theorem, has a specific meaning. We often use the term likelihood, basically I think, as a synonym for probability. We say, what's the probability of this or that happening? And we mean that to be to have exactly the same meaning as if we had said, what's the likelihood of this or that happening? But likelihood means something very different. You'll notice it's the inverse It's an inverse conditional probability. You see that, in other words, the A's and the B's are switched. This is going to be important because the thing that takes the A position is the thing we're most interested in. The thing that we're interested in the question of how well it is supported by the evidence that appears in the B slot. So the posterior probability is the probability of the hypothesis in light of the evidence, and the likelihood is going to be the probability of the evidence given the truth of the hypothesis, and that's a very different thing. I'll explain these terms later and the important uses to which they're put in just a moment. To see how Bayes' theorem is derived, and derived very simply, we need to look at just a couple of very basic definitions that we've already seen from the mathematics of probability. So statement number one here is simply the definition of conditional probability. The probability of A given B is simply the probability of the conjunction of A and B divided by the probability of B. when you think back to the area diagrams that I used to try to explicate the meaning of certain basic probability notions, the terms on the right-hand side of this equation are saying, let's look at the fraction of area that's both an A and a B area within the overall B area. The second statement you have here is simply the definition of the probability of a conjunction and what that means. So the probability of A and B is equal to the probability of A times the probability of B, if they're independent, or the probability of, more generally, the probability of A times the probability of B given A. You may also remember that the probability of the conjunction A and B can also be given a different definition. And that's where the thing that appears on the right-hand side of statement number 2 is one where we simply switch to A's and B's. So the probability of the conjunction A and B is also equivalent to the probability of B times the probability of A given B. In any case, it's just the definition of the probability of a conjunction. One thing to notice is if you look back to statement number 1 and the right-hand side of the equation of statement number 1 and the numerator of the right-hand side, you'll see there that we have the probability of the conjunction A and B. And statement 2 is, of course, about the probability of the conjunction A and B. Well, this just means, of course, that you can take the right-hand side of 2 and plug it into the numerator of the right-hand side of 1. And that's Bayes' theorem. That's it. That's the whole different derivation. So you can see that in some sense Bayes' theorem is just fairly trivially falls out of statements 1 and 2. The fact that it trivially falls out of them, though, doesn't mean that Bayes' theorem itself is trivial. There's a lot of important uses to which Bayes' theorem can be put, and that's where the interest in Bayes' theorem lies. There is another formulation of Bayes' theorem that you sometimes see, and in fact that I'll show you on a later slide. And that later formulation is simply statement number 3, but where the denominator of the right-hand side is broken up into pieces. The probability of B, as I'll explain, is equivalent to the appearance. Let me back up. Think about the area diagrams that I was using, and I would have some of the area represent A, some of the area represent B, and you may remember that some of the B areas were disjoint in the diagrams that I produced. In other words, there'd be a little B over here in the A part of things, and then there'd be a little B area over here in the not A part of things. That means that the overall area of B is equal to the B that's over here, and then the area of the B that's over there. So the other formulations of Bayes' theorem take that approach. The probability of B is the equivalent to the probability of B within A, and the probability of B within not A, where those two things are summed together. So whenever you see a more complicated looking formulation of Bayes' theorem, all they've done is they've broken the B part into pieces, sort of ordinary pieces. For the time being, we'll just stick with this more simple formulation. If you need to calculate the probability of A given B, you can use statement 1, you can use statement number 3. It's all going to depend upon the form in which your evidence appears. Like if you look at statement number 1, the right-hand side of statement number 1 does not include any conditional probability statements. But if you look at the right-hand side of 3, one of the terms is a statement of conditional probability, a likelihood value in particular. So depending upon how the pieces of information that you have are presented, well, then maybe you use 3, maybe you use 1, if you need to solve for the probability of A given B. But neither is really, when it comes to solving, strictly speaking, for the left-hand side of 1 or 3, either one is perfectly fine. It just turns out that the formulation of 3 winds up being very useful for a lot of purposes in philosophy, and other areas. So let's apply Bayes' theorem to a simple case first. A case that's so simple that it's not really going to show you how to appreciate the importance of Bayes' theorem, but it's good to start with the simplest case first. So let's think about the probability that a randomly drawn card from a standard deck of 52 cards will be an ace, given that it's a heart. Okay, so we're going to say, granted, or on the assumption that it's a heart, what's the probability that it's an ace? And this is something, of course, that you can figure out on your own without having to go through an equation, but let's just see how it works. On the right-hand side of this equation, you're going to plug in ace every time there's an A and heart every time there's a B. So in the numerator of the right-hand side, the probability of A becomes the probability that there's an ace. So what's the probability of the ace within the overall sample space, which is the probability of an ace within the overall set of 52 cards? Well, there's 4 aces out of 52, so 1 over 13. Then the next term in the numerator is going to be the probability of a card being a heart, given that it's an ace. So we're going to work a little bit backwards. So start with the right-hand side of that expression, the ace part. So how many aces are there? There's 4 aces in a standard 52 deck of cards. How many of those are hearts? 1. So the probability that a card is a heart, given that it's an ace, is 1 out of 4. So the numerator is going to be 1 over 13 times 1 over 4. And then the denominator is going to be the probability that a card is a heart. And again, since this is an unconditional probability, this is the probability within the overall sample space, which is 52 cards. So the probability of a card being a heart is 1/4. Okay, so we plug these in. 1 over 13 times 1/4 over 1 over 4. And the two 1/4s, of course, cancel out. And you get 1 over 13, which you might have been able to figure out on your own. But it's important to sort of go through plugging in the bits so you can get a little bit used to it. So let's turn our attention now to a more interesting case, a case that involves thinking about Bayes' theorem in the context of the evidential support that some information gives to a hypothesis. So I've replaced the A's and the B's here with H's and E's. So the H is the hypothesis that's of interest, and the E is the bit of evidence that we have before us. So on the left-hand side, we have the probability of H given E. That's just the probability of H in light of the evidence. That's the sort of central evidential question we want to ask about the relation between hypotheses and evidence is how probable does some evidence make the hypothesis. On the right-hand side, we have a few different terms, 2 prior probabilities and 1 likelihood value. In the numerator, we have the prior probability of H. Now, for the time being, you should not interpret this as being the probability of H prior to being in possession of any evidence or any information about anything in the world. We're going to address the question a few slides from now about how you should interpret the prior probability of some hypothesis before you have any information of any kind. For the time being, let's just think of the prior probability in this fashion. That's the prior probability of H is going to be the probability of H in light of other things we know, other evidence and other information. But just what that other evidence and information doesn't include E. So right now we're going to include, we're going to make E be some new piece of evidence we've just learned. This kind of situation where you've learned a new piece of evidence and you want to factor it in and see how it affects or should change the way you view hypothesis, is the primary way that Bayes' theorem gets used for understanding the confirmation of scientific theories for epistemological purposes. So that's what we'll start with right now, and then later we'll return to the question of how do you understand the prior probability of H when there is no evidence of any kind that seems to bear on it, sort of from the perspective of somewhat ideal beginning to inquiry. Okay, so that's the prior probability of H. The other term in the numerator is going to be a likelihood value. It's the probability of E given H. This concerns how surprising or unsurprising the evidence is in light of the hypothesis. Like if the hypothesis were true, what would it lead us to expect? If a hypothesis is true, it's going to make predictions about what we should observe. If we observe something that the hypothesis says we should observe, then the probability of E given H is going to be quite high, near 1, perhaps equivalent to 1, if the hypothesis entails those observations. Generally, a hypothesis is not going to entail any observations without the support of a bunch of auxiliary assumptions. But some of the time, of course, we have a hypothesis and a bit of evidence comes along, and it's not at all what we would expect if that hypothesis were true. So these are situations that we're going to represent as where the likelihood value is low, where the probability of E given H is low. We would not expect, we would not predict E if H were true. So that's the likelihood value. The denominator on the right-hand side of this equation is the prior probability of the evidence. There's different ways that this can be understood. And in an example that I'm about to give you, we're going to see that some of the time the prior probabilities, both of H and E, can be understood as background frequencies. So we have information about certain background frequencies that we already have. I'll give you an example of that where H and E are both, there's some background frequency, like how often does this disease occur? How often, how common is steroid use within the overall sample space? So both of these unconditional probabilities, remember, are in some sense conditional probabilities where the part to the right of the unspoken bar is simply the entire sample space. So some of the time we do have a sense of what is the frequency of E or H within the overall sample space. Some of the times we actually lack this background information. So I think that's enough for right now. Let's move on with the example I was going to give. So suppose there are two weightlifting teams, teams A and B. Let's suppose they're from the same university. For whatever reason, the university just has two teams. And one of the weeks, it will send Team A, and then the next week it will send Team B to the competition. And then the following week after that, A and then B, and then so on, alternating. Okay? And let's suppose that the two teams differ with respect to their steroid use. So these differences of frequency of steroid use can be represented as conditional probabilities. So the frequency of steroid use within Team A, we're going to represent with this conditional probability. The probability that X is a steroid user, given that X is from Team A, is how we'll understand that frequency. And in the case of Team A, the frequency of steroid use is 0.9, or 90% of the members of the team of Team A are steroid users. Not cool. Team B is much better. They still have some steroid use, but it's not so bad. So the probability that a given athlete, X, the variable here, X ranges over athletes, X is a steroid user, given that X is from Team B, is only 0.2. So there's some steroid use. Not so bad. So now let's consider a particular hypothesis. Let's consider the hypothesis, which we'll call H sub A. This is the hypothesis that some randomly selected athlete is from Team A. We can compare this to some other hypothesis, the hypothesis that randomly chosen athlete is from Team B. In the present case, our E is going to be this equivalent to the statement X is a steroid user. Now let's consider this probability statement, the probability that our hypothesis HA is true. HA, you'll remember, is the probability that some randomly chosen athlete would be from Team A. Now imagine that we're in a situation where we don't know which week it is. We don't know any further information. We do possess the information, the background information, which says Team A and B alternate participation weeks. One team participates this week, the other team the next. We know that, but suppose that we don't know which week we're on. Like, if we knew who competed last week, if we knew that Team B competed last week, then the probability that some randomly chosen athlete from this week's competition would be from Team A would be 1. We would know pretty much for sure that if we would know that this probability value would be 1, but it wouldn't exactly be a prior probability value based only on our background information about frequencies. It would be, that's a situation where we would have a conditional probability. We would be evaluating the probability of HA given our knowledge of which week we're in and who competed last week. But suppose we don't know who competed last week. And we just want to know what's the prior probability that this week some randomly chosen athlete would be from Team A. Well, this kind of reduces to this question. What's the probability that A is competing on some randomly chosen week? And it's easy to see that both of these probability values should be 0.5. Now let's consider this probability statement. The prior probability of E. Now E, you'll remember, is that X, some randomly chosen athlete, is a steroid user. So let's again assume that we don't know which week we're on, so we don't know who's at the competition. So you remember that we do have information about how frequent is steroid use within Team A and Team B. So if we knew which team was competing, then we would be able to have a sort of better idea of the probability that some randomly chosen athlete from this week's competition would be a steroid user. But suppose for the time being that we don't know which team is competing. We know the background rates of how often the teams compete, and we know the background rates of steroid use within each team. In this kind of situation, what would be the prior probability value that some randomly chosen athlete would be a steroid user? This is a situation where we don't know if we're drawing this randomly chosen athlete from Team A or Team B. So how would we figure out this value? Well, we'd have to take into account both the frequency of steroid use within Team A and the frequency of steroid use within Team B, and then take something like an average to determine the probability that some randomly chosen athlete from our overall set of athletes, composed of Team A and Team B athletes, is a steroid user. So we would calculate it something like this. The frequency of steroid use within Team A is 0.9, or 90% of them use steroids. The frequency of steroid use within Team B is 0.2, or 20%. Now, since these two teams have the same number of members and compete equally often, the probability that some randomly chosen athlete on some randomly chosen week would be a steroid user is going to be the value calculated by this equation. Because the teams' sizes are equal, frequency of competition is equal, we're going to give equal weight to the 0.9 value and the 0.2 value. Those are the steroid frequency rates within the teams. But we're going to multiply each by 0.5 as a way of giving them equal weight. If one team competed more often or had more members, we would need to adjust these weights to give more weight to the team that competed often, or more weight to the team that maybe had more members. But they're equally sized, equally frequently competing. So this works out to be 0.5. So it's 0.45 plus 0.10. Okay, so within the overall sample space of athletes, the frequency of steroid use is 0.55. Now that frequency of steroid use is not evenly distributed over the overall sample space, right? There's more steroid use concentrated in Team A and Team B. But when you're not worried about the density of the distribution, like that the density or frequency of steroid use is more frequent or denser within Team A than Team B, when you're not worried about that, you're just saying, well, on the whole, on average, across the whole, what's the average frequency of steroid use? Well, it just works out to be 0.55. So now let's ask about this kind of situation. Some randomly chosen athlete at this week's competition has tested positive for steroids. What's the probability that this athlete is from Team A, given that they're a steroid user? Okay. So suppose that you don't have information about which team is competing this week. Again, if you knew which team is competing this week, then we would know what the probability is that this athlete is from Team A, right? But if you don't know that, and what you do know are the background rates. In our last slide, we calculated the background or overall rate of steroid use across the sample space. And we also have background information about how often the teams compete and how frequent is steroid use within each team. From all those facts alone, we can calculate this probability value. The probability that X is from Team A, given that X is a steroid user, even if we don't have in our hands a schedule that says this week's competition features Team A. If we don't have that, we can still come to a pretty good idea about the probability that this athlete is from Team A. So here's where we really are going to apply Bayes' theorem. What we've done so far is kind of warm up to this. So we're going to take Bayes' theorem, the probability of our hypothesis, given our evidence, and we're going to break it into its pieces. But the pieces are going to be the ones that are relevant here. So instead of H's and E's, we're going to have the particular hypotheses we're interested in and the particular bit of evidence that we have. So substituting in for Bayes' theorem, we have on the right-hand side, in the numerator, the prior probability of H, which in this case, our hypothesis is that X is from Team A. Then we're going to multiply this in the numerator by the likelihood value. This is the probability of E given H. So our E's concerns steroids, and our H concerns the team. So this is equivalent to the probability that a randomly chosen athlete is a steroid user, given that they're from Team A. And we already know that. Remember, A is the steroid-using team, 90% of them. So in the denominator of our substitution instance here is going to be the probability of E, which in our case is the probability of steroids within the overall sample space, which we calculated on our last slide as 0.55. So what is the prior probability that X is from Team A? That's just the general frequency with which Team A competes. That's 0.5. What's the likelihood value, the probability that an athlete is a steroid user given that they're from Team A? Well, that's 0.9. 90% of Team A members are steroid users. And then the denominator is the 0.55 value that we calculated on our last slide, the overall frequency of steroid use in the sample space. So this works out to be 0.45 over 0.55, which is about 0.82. So our prior probability value was 0.5. The posterior probability value is about 0.82. So let's think about that. And we'll be able to think about why it is that the labels prior and posterior are very appropriate when we think about this. So before we have this bit of evidence that some randomly chosen athlete from this week's competition has tested positive for steroids, before we had that piece of information, our best guess as to whether some randomly chosen athlete from this week's competition is from Team A, our best guess was just 0.5, so that's our prior probability of our hypothesis in question. But then we're presented with some new information. By the way, this randomly chosen athlete, steroid user. Oh, now we can sort of update our belief, as it were. Our belief initially was just, well, the prior probability that this athlete's going to be from A is just 0.5. Oh, but now you tell me that this person is also a steroid user. Oh, now I'm going to up my probability estimate. And Bayes' theorem tells us how to up, raise, or lower, or whatever, our probability estimates as new information comes in. Notice that the 0.82 value lies midway in between 0.5, our prior probability value for H, and our likelihood value, which is 0.9. The likelihood value is, it tells us how many steroid users there are on Team A. That's 90%. It's not right to think, oh, 90% of team members on Team A are steroid users, and you've randomly selected someone from this week's competition who's a steroid user. Oh, the probability that person is from Team A has got to be 0.9. That's not right. I mean, you should be thinking it's from 0.9. You should be thinking that the athlete is from Team A. Right, that's the steroid using team. I mean, the overwhelming majority of them do use steroids. So you should be suspecting it's Team A. But how strongly you should suspect that should not be equivalent to the 90% value, that is, the 90% frequency value within of steroid use within Team A. And the reason why it shouldn't be so high is because that team member, that athlete who was randomly chosen and happened to test positive for steroids, they might actually be from Team B. So your estimate has to be tempered a bit by that other piece of information, that they might be from Team B, which, yes, there are steroid users there. So it's not impossible for this steroid user, randomly chosen athlete who tested positive. It's not impossible for them to come from Team B. So our conditional probability value there at the bottom of the screen that's equal to 0.82 gets tempered a bit by the fact that, yeah, this is probably someone from Team A, but might be Team B. And so Bayes' theorem is just a way of putting all this information together and telling us exactly to what degree we should temper our guess that the athlete is from Team A. So that's Bayes' theorem at work. Here is the more complicated version of Bayes' theorem, listed below the simpler form of Bayes' theorem. On an earlier slide, I mentioned that more complicated formulations of Bayes' theorem have a more complicated denominator on the right-hand side. And in the present case with steroid use, it's easy to see why the probability of E should be broken up in just this way. Remember, in our steroid use case, the unconditional probability of E is just the overall frequency of steroid use across the sample space of athletes. Look at the denominator of the more complicated formulation. The left-hand side of this denominator is just saying, well, in order to determine the overall frequency of steroid use, we've got to take into account steroid use within Team A and the steroid use within Team B, and take into account that these teams don't use steroids equally often. So where H is the hypothesis X is from Team A, and where not H is the hypothesis X is not from Team A, which in our present example means they're from Team B, what we get on the left-hand side of this complicated denominator is the probability that an athlete is a steroid user, given that they're from Team A, multiplied by the sort of frequency of A-team athletes within the overall set of athletes in question. And then we're going to add that to the probability that we have a steroid user, given that they're not from team A, i.e. they're from team B, multiplied by the overall frequency of team B members within the overall set of athletes in question. So this equation that's on the bottom, the more complicated version of Bayes' theorem, can sometimes make students' heads spin. But when you think about it in light of our steroid example, I think it makes a whole lot of sense. Okay, so moving forward a little bit, I want to contrast Bayes' theorem with other kinds of ways of thinking about evidence, other pieces of advice that people have formulated for how you should make guesses about frequencies from presently available information. So an early 20th century philosopher, Hans Reichenbach, offered what he called a straight rule, which I think is a bad rule, and I guess most everybody thinks is a bad. Well, I think it's an understatement to say that most everybody thinks it's a bad rule. But the way in which it's bad will be illustrative of something important. It will throw into relief a strength of Bayes' theorem. So Hans Reichenbach was part of the, I don't know if he was ever called a logical empiricist, or I don't think he was part of the Vienna Circle. I could be mistaken, but he sort of hung out with those kinds of guys. So think about early 20th century positivists, logical empiricists, people who really loved math and science, and he wanted to formulate he was part of a movement to make philosophy very rigorous and as mathematical and scientific as possible. Okay, so that's who he was. So, suppose the hypothesis that we're dealing with it concerns the long-run frequency of heads, where we're going to be tossing some coin over and over again, and we're going to try to estimate what this long-run frequency is. So our guess about what that long-run frequency is going to be X. And suppose that we have some observations about the frequency of S within some frequency of heads within some sample. So we've been tossing the coin, and we have an observed frequency. So we have an observed frequency, Y, and we want to figure out how to use our observed frequency to make a guess about the long-run or true frequency of heads should this coin tossing go on ad infinitum. So Reichenbach has a suggestion. Right? I mean, it couldn't be simpler than this. If your observed frequency is Y, well, what you should do at any point is assume that X equals Y. So your estimate about the long run or true frequency of heads within some infinitely extending series of coin tosses should just be whatever the frequency is in your sample so far. Okay? So you don't need to modify your sample. Sort of take what you've observed as the frequency within your sample and do anything to it, perform some calculations, modify it anyway. Just say, I've observed frequency Y, so that's what I think the overall value is. So this seems to be pretty lousy as a rule. So at the very beginning, when I'm tossing a coin for the first time and it lands heads, what's the frequency of heads? Frequency of observed heads within my sample of 1. Well, it's 1. 100% of the 1 tosses I've made have come up heads. So the straight rule says, well, go ahead and assume that the overall or true frequency of heads in the long run is 100%. That's pretty dumb, right? I mean, it's a coin with two sides. I'm going to have to assume that the overall frequency is 100%. That seems kind of crazy. It seems crazy to assume that that's the overall frequency with any amount of confidence. I tossed the coin twice, and instead of it coming up one heads, one tails, it happens to come up heads both times. So again, my y value, my observed frequency, is 1. 100% of observed tosses come up heads. So this seems pretty lousy. There's no way in Reichenbach's straight rule to incorporate information like the following. What if I have some reason to believe that the coin is fair before I toss it? How does that figure in? Reichenbach's straight rule sort of has nowhere to plug that in. There's sort of no... There's no room in the equation to sort of plug in this value of background information. Or even if I don't have any reason to believe that the coin is fair, I can at least see that the thing's got two sides, and I've got a little knowledge about physics. So even if I don't believe the coin is fair, but I just believe it's two-sided, such that it's possible for it to come up on either side, I'm not going to believe that 100% of the time it's going to come up heads. So let's return to Bayes' theorem to see how it unlike the straight rule, there's a place in Bayes' theorem for background information to figure in, and then there's a place in Bayes' theorem for information about your present observations to figure in as well. In Bayes' theorem, our present observations are going to be represented by E, and then our background information, background beliefs, are going to figure into our estimation of the prior probability of H. So suppose in a coin tossing example, I have some background reason, some reason for thinking that the coin is fair. Before I toss the coin, before I see any observations, like the observations that I might see might be that, well, I toss a coin 10 times, and 5 out of those 10 times it comes up heads. Before I toss it, I might have some background reason for thinking that what I have here is H is true. That's where the long-run frequency, or the true frequency of heads, is 0.5. I might have some reason for thinking that H is true. The probability of H is going to be quite high if I have some reason. If I know it's just an ordinary coin, if I've been told by the person who hands me the coin that it's fair and I think they're being trustworthy and sincere, they're not trying to mess with me. So the prior probability of H is going to be quite high. Don't be thrown off by the fact that I have the prior probability of H being high, and then I have a 0.5 value appearing within the statement of what H is. 0.5 is not a high value on a scale from 0 to 1. What's high is the likelihood that the true value is 0.5. So we actually have two kinds of probability values working here. When I say the prior probability of H is high, I mean something about my subjective degree of belief. When I say the long-run frequency of head is 0.5, I mean something about, it's not about my degree of belief. It's about a frequency. I have my degree of belief about the frequency. But in any case, I'm going to assign a high prior probability to H before I toss the coin. Once I do toss the coin and I see 5 out of 10 heads, I'm going to say, oh, see, just as I suspected, this certainly looks like a fair coin. Consider the likelihood value in this kind of case, the probability of E given H. In the present case, E is that the observed values in our sample would be this, 5 out of 10 heads. And H is that it's a fair coin. Is E what we would expect given H? Absolutely. I mean, if you have a fair coin and you toss it 10 times, you're not going to get 5 out of 10 every time. But getting 5 out of 10 is absolutely unsurprising. It's the most unsurprising thing you could have as a result if the coin is fair. So the probability of E given H is quite high. So in the present case, My prior probability for H is 0.5. Before I toss the coin, I have some reason for thinking that the coin is fair. So I already assign a high probability to H. Then I witness 10 coin tosses, and I see 5 out of 10 of them being heads. This doesn't really change my belief, let's suppose. It might, I suppose, confirm my prior belief to some small degree. So I might have a little bit more confidence that H is fair. So if you look at the sort of red statement there at the bottom, I guess it's possible for the right-hand side of that to be a little higher. I guess it all depends on how strong my prior probability value was. If my prior probability value wasn't that high, then seeing this piece of evidence should raise it some. But if my prior belief in the fairness of the coin was already pretty high, then seeing 5 out of 10 coins may not do anything at all. So the reason why I wanted to say something about Reichenbach's straight rule and then use that to contrast the straight rule with Bayes' theorem is because you see that we have somewhere in the equation to plug in background information, prior information. Reichenbach says what you should conclude about your hypothesis is only what your present observations tell you. Well, observation is certainly important. All scientific theories must answer to observations. All empirical beliefs of any kinds, even if they're not scientific theories, must answer to observational evidence. But in addition to any set of present observational evidence, there's going to be your background beliefs, and you can't ignore that. On the following slide, I'm going to give you an instance of straight rule thinking, which I think is mistaken. And then in further slides, I'm going to give you some examples for how background information really matters. Even if your present information says one thing, there could be reasons for being suspicious, for dragging your feet a little bit. I mean, there can be very good reasons that are perfectly rational for not totally following your present evidence. And the straight rule thinking that Reichenbach recommended says only follow present evidence. So New York Times lifestyle articles seem to repeatedly follow straight rule thinking. And I've been amazed at how bad so many of these articles are, or how annoying to me they are anyway. You know, when it comes to covering matters of international politics, important current events, you know, the New York Times may still be, you know, our nation's best newspaper. But when it comes to questions of should you stretch before or after exercise, is wine good or bad for you, should you lie to your significant other, lifestyle articles, I think the New York Times is absolutely annoying for a lot of reasons, only one of which is straight rule thinking. So here's a common thing you see. And it's obviously not just the New York Times. It's you know, a variety of clickbait sorts of articles that you might see out there. The article says, well, the received wisdom is this. The received wisdom about whether you should stretch before or after exercise and what kind of stretching should it be is this. But some new study, one random expert from nowhere land, says not X. So what does the lifestyle article recommend? They recommend that you totally throw out all received wisdom, everything you've ever known about relationships, about falling in love, about wine, saturated fats, red meat. And you should base your belief now solely upon this new study. I find this to be terribly annoying. It's a mark of rationality that you respond to new evidence and information. Being reasons responsive is talked about by philosophers who work in ethics and action theory. We don't really use the word reasons responsive, I guess, in epistemology, but we use the idea. I mean, when new evidence comes along, what should you do? Well, change if the new evidence says change. But the thing about it is the straight rule thinking and the New York Times lifestyle articles say you should change totally and completely, whereas Bayes' theorem says you should put together your background information together with the new information. And change, yes, but the more strongly, the more well-confirmed the received wisdom is, well, then the less you should change. Now, if the received wisdom, the background information is not so strongly well confirmed, then maybe you should change to a larger degree. Bayes' theorem tells us exactly how to combine them, whereas the straight rule thinking says don't combine background information and new information at all, go only with the new information. So it's a huge strength of Bayes' theorem, that it allows a place for both and tells you to what degree you should modify in light of new information. Now let's look at a coin tossing case where present observations conflict with background belief. A minute ago I gave you a case where you had a prior belief that the coin was fair, and then the observations that you see completely fit with that background belief. You see 5 out of 10 coin tosses coming up heads. Well, that's exactly what you would expect if you do indeed have a fair coin. But now let's look at a case where you have a background belief, but then your present observational evidence conflicts with that. So H is the belief that the long-run frequency of heads is 0.5, i.e. that the coin is fair. So let's suppose that you do indeed have a reason, prior to tossing the coin, to believe that it's fair. So the probability of H is high. But let's suppose now that what you observe is represented by E in red. You toss the coin 10 times and it's 10 heads in a row. And now let's consider the second red statement. The probability that this observation is what you would see if the coin really is fair, i.e. if H is really true. 10 heads in a row, is that really what you would expect to see if the coin is fair? No. So this likelihood value, the probability of E given H, is going to be quite low. So in this final statement on the slide, we have Bayes' theorem recommending to you that you should adjust your background belief. You had this prior probability, this prior belief in the fairness of the coin. That belief needs to go down. Is it absolutely impossible to toss a fair coin 10 times and get 10 heads? Obviously not. It's just unlikely. So your belief should not be totally extinguished, because what you observed is not absolutely impossible. It doesn't totally put some kind of nail in the coffin of your prior belief, but it should go down. So the right-hand side of the bottom statement here on our slide is the posterior probability. The posterior probability, the posterior belief in the fairness of the coin in light of what you just witnessed. In light of what you just witnessed, this belief should go down. So, okay. So you can combine your prior belief with your present evidence. It's not like the straight rule is the only rule that says you should pay attention and maybe pay a lot of attention to present observations. Bayes' theorem doesn't say don't pay a lot of attention to present observations. It just says pay attention to that and background beliefs and combine them for the overall verdict. The overall verdict is the posterior probability value, the probability of H given E. I now want to consider the application of Bayes' theorem to a more philosophically controversial set of hypotheses. So we've seen how Bayes' theorem can be used to figure out how likely it is that the steroid user is from Team A rather than Team B. And we've seen a little bit on how maybe you should update your beliefs, your prior beliefs in light of present evidence. If you have some prior belief in the fairness of a coin, but then you witness one thing, well, your beliefs should shift and update in one direction. Not maybe all the way in one direction, as far in one direction as Reichenbach's straight rule would have us believe, but you should maybe go in that direction. So now I'd like to consider a case of applying Bayes' theorem to design arguments. So there's three sets of traditional arguments for the existence of God: ontological arguments, cosmological arguments, and design arguments. And no form of cosmological or ontological argument for the existence of God uses Bayes' theorem, but design arguments all do in some way. So let's just briefly consider a word about this. So let's consider two very simply defined hypotheses. I have hypothesis 1 as God exists, and I shall stipulate that what I mean by God is a tri-omni being. Omnipotent, omniscient, omnibenevolent, all-knowing, all-powerful, perfectly good God. Note that H1 makes no distinction between Jewish, Christian, Muslim, or any other kind of omni-being. H2 I have represented as no God, but what I have in mind is something like there's just natural processes, unguided natural processes. So, in design arguments, what the design arguer does is they look at some features of nature and suggest that these features of nature provide some degree of confirmation for there being a creator. Very commonly these days, the cosmic fine-tuning argument for the existence of God is a very common version of a modern, updated version of the design argument. You look around and you see how things are just right for life. Out of all the possible values that the fundamental constants of nature could have taken on, they've taken on just those values which fall within a Goldilocks zone, not too high, not too low, not too strong, not too weak. If the strong nuclear force were even the slightest bit stronger or the slightest bit weaker, life would not be possible. If the electromagnetic force were the slightest bit stronger, slightest bit weaker, life would not be possible. And these aren't merely, I'm not going to rehearse the fine-tuning argument here, but these are not merely arguments that try to say life as we know it wouldn't be possible. I think they're rightly interpreted as making the argument that life would not be possible. For example, if you made the strong nuclear force is denoted by the constant epsilon with a value of 0.007. If you were to make this value 0.006, I believe it's the case that the periodic table of elements would consist only of hydrogen. There would be no elements beyond hydrogen. It's not just that life as we know it wouldn't be possible in this kind of scenario. Life wouldn't be possible. You can't make life of any kind if you just have a periodic table of, you have no elements in nature other than hydrogen, one proton in the nucleus. In order to have life, you have to have metabolism and replication. Metabolism understood very broadly as all of those life processes dedicated to preserving life, preserving the thing as a thing distinct from its surroundings, and then making copies of itself in some sense. You can't build anything that does all that if you only have hydrogen building blocks. In any case, there's a variety of fine-tuning bits in nature you might point to. You might try, like Michael Behe, to boneheadedly point to what's called the irreducible complexity of certain molecular structures. In any case, you point to something, some bit of evidence that isn't allegedly what you would expect if there's no God. So you compare two values. What is the probability that we would see everything, all these factors in life being just right for the possibility of life if there's a creator omnigod at the controls? And let's compare that likelihood value to another one. The probability that we'd see all this fine-tuning stuff, the world is just right over and over and over again, if there's no God at the controls. And so the claim is that one likelihood value is considerably higher than the other. You might read philosopher-biologist Elliot Sober on this topic to look at some important objections to these claims. I won't go into them right now. But in any case, the claim is fine-tuning, things being just right, is exactly what we would expect if there's a God, but it's not what we would expect if there's no God. So these likelihood values are different. Okay, now these likelihood values, of course, appear in the numerator of some substitution instance of Bayes' theorem. When a value in a numerator goes up, well, the value of the whole goes up, right? When the value in a denominator goes up, right, the value of the whole goes down. So, the claim is, because this likelihood value in the top right, the numerator, goes up, then the posterior probability of the existence of God in light of fine-tuning evidence goes up, such that the hypothesis of God's existence receives some degree of confirmation from the fine-tuning evidence, and that the hypothesis of this kind of God's non-existence receives some degree of disconfirmation in light of this evidence, in light of the fine-tuning evidence. Since this evidence provides a boost for one hypothesis and an anti-boost for the other hypothesis, the claim from the design argument is that this evidence favors one hypothesis over the other. So that's how design arguments are supposed to work. There's important questions about whether we can really make sense of these likelihood values in the proper way, but here's one point to take into account. In order to sort of argue for the existence of God, it's not enough that some substitution instance of Bayes' theorem, that it be shown that the likelihood value that appears in the numerator is high. Just suppose, let's just grant for the sake of argument, that the likelihood value E given H1 is high. At the end of the day, I don't think you should think that it is actually high. But if we grant that, suppose we grant that fine-tuning evidence is such that its conditional probability is high, given the existence of God. That only shows that one term in the numerator is high. You also have to take into account the other terms, specifically things like the other term in the numerator. So you can have a very high likelihood value, but if the prior probability of the hypothesis that we're dealing with is extraordinarily low because it's an implausible hypothesis, then on the whole, what is the posterior probability of your hypothesis given your evidence going to be? It may not be very high at all. A high likelihood value is only part of the story. But you take a high likelihood value and multiply it by a very low prior probability value for the hypothesis, and you may not get something that's very high at all. Here's just a brief example taken from Elliot Sober, who helped put philosophy of biology on the map a couple of decades ago. This is from his book Evidence in Evolution. Very difficult book to read. But chapter 2 of this book, he looks at design arguments. Suppose you hear a loud noise in the attic. That's your evidence, your present set of observations. You hear a loud noise. Now let's consider the hypothesis that gremlins are bowling in your attic and that this is what caused the loud noise in the attic. I don't even know what a gremlin is, but anyway. H. Gremlins are bowling in the attic. What's the likelihood value here in question? The probability that there would be a loud noise in the attic if, in fact, gremlins are bowling in the attic. You have to agree, regardless of your beliefs about the existence of gremlins, you have to admit that this likelihood value is very high. You have to admit that. If there really were these things such as gremlins, and if they really were bowling in my attic, this likelihood value is going to be high. Bowling gremlins will make loud noises in attics high. Of course, the prior probability that there really are such things as gremlins and that they bowl in attics is extraordinarily low. So this is sort of the part where it's one of the places where the flying spaghetti monster makes an appearance. What's the probability that we would have fine-tuning of it? That we would live in find ourselves in a finely tuned universe, a universe finely tuned just right for life, given that it was created by an all-powerful, all-knowing flying spaghetti monster. That likelihood value is high as well. So, in any case, just a bit about likelihood values and design arguments and how one place where flying spaghetti monsters fit into Bayes' theorem, the prior probability of there actually being a flying spaghetti monster is, of course, negligibly low. Let's talk about Bayesian conditionalization now, a bit more straightforwardly. I've already talked about it. I've already warmed you up to the idea. Bayesian conditionalization is just a set of advice about how you should update your belief in light of new evidence. And I've already been talking in conditionalization terms. I just haven't laid it all out quite like this. So initially you have some belief in H, your prior belief in H. Okay? Then some piece of information comes along, E. And you now look at your belief in H in light of this new piece of evidence. And as we saw before, sometimes you need to adjust upward, adjust downward. We saw a case where you initially believed a coin was fair, and then you saw 10 out of 10 coin tosses being heads. The rational thing, according to Bayes' theorem, and I just think just intuitively rational thing, is you should be less certain now that the coin is fair than you were beforehand. So you should adjust your belief in the fairness of the coin downward. In the design argument, if you had some prior belief in H, and then you learn about fine-tuning facts, you should adjust your belief in the existence of a creator God upward. And by the way, that still remains true even if the prior probability that you assign to the existence of a creator God is extraordinarily low. You assign a very, 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 very low prior probability value to the existence of a creator God. Once you see that the likelihood value is in question is high, where that likelihood is the probability of the evidence, fine-tuning evidence, given the existence of a creator God, once you see that that's high, I actually think you should adjust your probability upwards. It should provide some degree of confirmation to the existence of a creator God. Now, the issue, of course, is that I think the fine-tuning evidence also provides some degree of confirmation to a spaghetti monster creator being as well, and many other implausible hypotheses as well. But in any case, when you learn some new piece of information, Bayes' theorem shows you how to combine your background beliefs and your present evidence to come to some new conclusion. So you had your prior probability of H, and now you have a posterior probability for H. Well, Bayesian conditionalization is this bit, which I haven't exactly mentioned before. Not exactly, almost. This is, now that you've learned E, you should change your prior probability your prior belief in H, you should change it now, such that now when someone asks, hey, what's your prior probability for H? You should sort of fold in E into H, as it were, such that now at time 2, what you now call your prior probability for H is equal to your posterior probability for H a minute ago that you calculated using your previous, at time 1, prior probability for H. So you have one belief in H, E comes along, and you see the posterior probability of H given E. Well, you should let that posterior probability now be your new prior. This is updating your prior. Okay. Because new information is... You have a prior probability for H, you learn something. You calculate the posterior probability, then you update such that you now have a new prior probability for H. But then you learn something else. First of all, you learned E1, now you're learning E2. And now you're going to calculate a posterior probability value, which appears there on the right-hand side of that equation. The posterior probability value uses P sub 2H. So you've got to and so Bayesian conditionalization says you need to update again. You kind of took E1 and you folded it into your estimation of E, folded it into your estimation of H. Well, you do that again now, and so on ad infinitum, such that now when you see P3H, P sub 3H, you now have your third prior probability value for H. So we have 3 prior probability values appearing on the screen. P1H, P2H, P3 of H. But as we're going through this process, it's a process of learning. When you're at P1H, this is before you ever learned E1 or E2. And by the time you're at P3H, this is in line of learning these things. And so no longer when someone asks for your prior probability of H, should you give the initial prior probability value that you gave at the very beginning of things, the P1H. It should now be this more informed prior probability value. So that's Bayesian conditionalization, updating your prior probability estimates in light of posteriors that you calculate. The next couple of graphs I'm going to give are going to show Bayesian conditionalization at work, the updating process at work. In this particular graph, we have 4 hypotheses that are being considered. There's 4 hypotheses. Using the principle of indifference, the person in question assigned to each of them an initial prior probability value of 0.25. So if you look at the far left-hand side of this graph, where all the points meet, they meet at 0.25. Each of these 4 hypotheses started out with a prior probability of 0.25 based on the principle of indifference. Along the x-axis, you see that these are updating steps 0 through 10. 0 is, of course, where we don't do any updating. Along the y-axis, we see probability values. So at updating step number 1, we see that the 4 hypotheses begin to diverge. So 2 of the hypotheses receive some degree of confirmation in light of the first piece of evidence. So 2 of those lines slope upward, one obviously more than the other. And 2 of the data curves, there's a slope downwards. And as we update again and again, update step 2 and 3, we see that one hypothesis really begins to become separated from the others. Although there is this one hypothesis which initially at step 1 received a tiny bit of confirmation at the first updating step, we see that it starts to go downhill after that. Okay, so Each updating step is a new piece of information, and as new information, new evidence is coming in, it's separating the wheat from the chaff. So confirmation and disconfirmation comes in degrees. One theory being fairly strongly confirmed by evidence as it's coming in, 3 other theories being disconfirmed, but not being disconfirmed to the same degree. That one theory on the bottom is really being put through the ringer. I mean, it's not faring very well in light of the evidence. Its values are going down towards 0, and they look like they're going to stay, excuse me, around 0. And the other the 2 theories that are in the middle, they are receiving disconfirmation, but they're not totally dead in the water. Nonetheless, there is a huge difference between the top theory and all the others. So this is Bayesian conditionalization. Updating in light of new evidence. Now, there's a question about what kind of initial prior probability should you assign to a hypothesis before you've begun the updating process, before you've begun to collect data that is relevant to it, that could potentially confirm or disconfirm it. So the most common form of Bayesianism is called subjective Bayesianism. It's not the only form. It's the most well-known form. Some people think it's the only form, but it's not. But let me start with it. Subjective Bayesianism says it doesn't matter what prior probabilities you start with. You want to use the principal indifference to assign prior probabilities of equal weight to all the relevant competing hypotheses? Fine. You want to pull prior probabilities out of a hat, out of a Cracker Jack box, flip a coin, anything goes. Subjective Bayesianism says there are, among other things, there are no constraints on prior probabilities. Where prior, I mean the very first prior probabilities, the initial prior probabilities. And the reason why they claim this is because of the power of the conditionalization process. The conditionalization process, as you update on piece of information after piece of information, has this property that it swamps the priors. So in this particular chart that you see here, you see a red and a blue curve. You see them converge, although they started out at very different points. So left hand, the y-axis are its probability values, and we're thinking of priors that are being updated by conditionalization. And along the x-axis are the number of times that there is updating. Strictly speaking, I should have a 0 as one of the. I should have a 0 point along the x-axis where you haven't yet updated. But imagine there being a 0 point, and you get the idea. We have, say, one theorist who assigns one high prior probability to the hypothesis in question. We have another theorist, let's say, who supplies a low prior probability, very low. But then we see both theorists update in light of new information about 20 times, and we see convergence. So in the previous chart, we had, let's suppose, one theorist, 4 theories. Now we have one theory, 2 theorists. Both are looking at the updating process. In the previous slide, we showed theories being separated, wheat from the chaff, by the conditionalization process. Now we're just looking at one theory, but different priors being assigned, and we see convergence. So this is called a swamping of priors. Begin with any prior in the world. You will arrive at the right value. Here I showed them arriving at a value of 0.5, but maybe the true value is 0.8. I could have drawn a chart where both lines converge at 0.8 or 0.2 or whatever the true value is. If you're committed to revising in light of new information in the right kind of way, ultimate starting points don't so much matter, actually. So that's subjective Bayesianism. Now there are a variety of features of objective Bayesianism out there. The key thing that distinguishes objective Bayesianism is they place constraints on the assignment of initial prior probabilities. They don't say any old thing goes. I mean, you have to have some kind of reason if you're going to assign an initial prior probability. Some people, like Elliott Sober, says, if you have a good reason for assigning an initial prior probability, yeah, go for it. Maybe it's a background rate. Like you remember when we dealt with the steroid weightlifting case, we had some stats about background rates. How often do these teams compete? What is the overall background prevalence of steroid use across the sample space of athletes? If you have some frequency data at your disposal that you can use to assign a prior probability, say, go for it. But Elliott Sober says if you don't have any kind of sort of empirically well-supported or otherwise well-supported reasons to assign priors in a particular fashion, then you have no business doing it, and you've got to do something else. And he's got some other theories about how you should understand theory confirmation, degree of confirmation by evidence as it comes in, if you're not able to assign prior probabilities. But in any case, objective Bayesians do something like what Sober suggested. Sober's not an objective Bayesian, but there's this kind of activity that says not any old assignment of prior probabilities will do. You've got to, there's constraints and there's got to be good reasons for the things that you do. But note that suppose you are very careful. However, that story, I'm not going to get into the story of what objective Bayesians think. You can just Google objective Bayesianism, find some brief summaries out there. But however the story is supposed to go, and however careful you are with your initial assignment of prior probabilities, swamping is still going to take over, or still going to be a very powerful factor. So as you continue to update and update after you very carefully and reasonably assigned your initial priors, the fact remains that what you're ultimately going to believe at the end of the day is going to be determined mostly by the evidence that you've updated in light of. So in any case, that's the swamping of priors. So there are about three things that make the Bayesian approach to epistemological matters distinctive. One is that degrees of belief can be modeled as subjective probabilities. And then the claim that theoretical rationality is a matter of a couple of things. One, that these subjective probabilities should satisfy the axioms of probability. This means things like if you believe A to degree 0.5 and B to degree 0.5 and they're independent and you believe they're independent, then you should believe the conjunction of A and B to degree 0.25 and nothing else. And so to satisfy the axioms of probability is just for your degrees of belief, your subjective probabilities, to sort of fit with all of the constraints on how probabilities should function that are specified by the axioms of probability. So this dimension of theoretical rationality is sometimes called synchronic rationality. So at any particular moment in time, your subjective probabilities at that time should satisfy the axioms of probability. If they don't, then this is a kind of probabilistic inconsistency or probabilistic incoherence. Think about logical consistency and inconsistency for a moment. Logical consistency is where all of the beliefs in the domain in question do not entail the negation of the others. They can all be true at the same time. When you believe A to degree 0.5 and B to degree 0.5, and they're independent, but you believe they're conjunction to degree 0.3, you're not exactly contradicting yourself. So it's not a logical inconsistency, but we can think of this as we can think of the problem from the perspective of Bayesian epistemology as being a problem that's kind of like a generalization of logical inconsistency. It's not an out-and-out P, not P. But there is a kind of inconsistency or incoherence when your probabilities don't combine in the right way. So in any case, this is the synchronic dimension to theoretical rationality. At a given time, your subjective probability should satisfy the axioms of probability. And then here's the diachronic element, which is instead of at a moment in time, we look at things across time. So across time, your subjective probability should be updated via the process of conditionalization that we've been describing on the previous slides. So these are really just the central features of Bayesian epistemology. There's lots of there's tons of big and complicated, deep theoretical questions we can ask about Bayesian epistemology. But these are basically the central features. You've got subjective probabilities, and then you've got these two views about proper constraints on probabilities. And that's Bayesian epistemology. What I'm going to turn to now are uses of Bayes' theorem which don't concern Bayesian epistemology. Like everybody, no matter what they are, Bayesian, frequentist, whatever, needs to understand how Bayes' theorem works, and with medical tests and a variety of applied domains. So I've kind of characterized Bayesian epistemology, and now I'm just going to focus for the remainder just on uses of Bayes' theorem. I want to say a few words about the interplay between background rates and present information in a way that is very practically relevant to a lot of lives. And it just gives rise to a certain kind of puzzle that I think every well-informed citizen needs to know about. So we saw that the straight rule from Reichenbach doesn't take into account background information at all. Bayes' theorem does a good job of that. There's this puzzle that arises. Some people call it a paradox. The surprising result that occurs when the background rates that you're dealing with are quite small. So if you're dealing with a rare disease in particular, is the most common common area where this is applied. If you're dealing with something that's very rare, and then you have a certain kind of piece of information that may very well be a very reliable and telling piece of information, if you put that very reliable and telling piece of information together with background information that says, oh, and by the way, the disease is really rare, a surprising result occurs, and I think everybody should know about this. Kahneman and Tversky, I think, are responsible for bringing this to light, or making this as well known as it is. I don't know who else. I think there could very well be some other important scholars who have been responsible for making this a fairly well-known issue. But Kahneman and Tversky, as we saw in their article, their very first article on heuristics and biases, is they think that people engage in what they call base rate neglect, or they commit the base rate fallacy. They fail to take into account background rates. So in their initial heuristics and biases paper, or their first famous heuristics and biases paper, they talk about how they tell people there is this sample of 100 people that we're going to draw from. 70% of them are engineers and 30% of them are lawyers. And they ask people what's the probability that any randomly drawn person would be an engineer. If you don't give them any further information, they follow the base rate information, which is just another way of saying the background information. And they say, well, if there's 70 out of 100 of them that are engineers, and you're just drawing randomly out of this group of 100 people, and you're not giving me any further information, then I'm going to say it's a 70% chance that the randomly drawn person will be an engineer. But Kahneman and Tversky then show that if you start giving people information, sometimes irrelevant information, or you just do much anything, and then Kahneman and Tversky suggested that the human tendency is to completely forget about this background information. I suppose connecting this up with my earlier slide, you might say that people engage in straight rule thinking there. They let only their present observation dictate their judgment or decision or belief, where Bayes' theorem tells you the right thing to do. You let your present observation, in combination with background information, tell you what the right thing to think is. So let's consider a case now of a disease that's fairly infrequent within the population. Here I have a case where I say, let's suppose that the probability that a woman has breast cancer is 1 out of 1,000. Let's suppose this applies to adult women in America over the age of 18. So let's say that 1 out of 1,000 of them has breast cancer. This isn't terribly far off the actual value, but I'm not sure exactly. I'm not completely certain about the actual value. So people who work in statistics and health statistics in particular call this the prevalence of the disease. Now, there's various tests for a disease. And anytime someone is talking about the accuracy or reliability of a test, they're talking about a conditional probability of some kind. So here's one kind of conditional probability. In the present case, the probability that someone tests positive for breast cancer, given that they actually have breast cancer. Let's suppose, for present purposes, that the test is a mammography, a mammogram, and that its sensitivity rate is 0.9. So sensitivity is a matter of how many cases does it catch? Something like that. Out of all breast cancer cases, out of all women with breast cancer who get a mammography exam, 90% of them are caught by the test in question. You test positive if you have it. So this is the sensitivity. Now, there are other conditional probabilities, however, that we need to consider. And this is the thing that maybe people don't know about. Our high school and college and even medical school, nursing school, educational systems don't seem to be set up so well to inform people about the rest of the story. So another kind of conditional probability that we need to be very concerned about is the false positive rate. So you have a false positive if you test positive for a disease, but you don't actually have it. So the positive part refers to what the test says. The test says positive. But the false part refers to whether that test is actually accurate or not. So you can have false positives, false negatives, and even true positives and true negatives. So if you look at the sensitivity rate, this is the rate of true positives. You test positive, and it's true that you have it. So people don't use the term true positive, but that often. It's more common just to refer to something like the sensitivity of the test and then the false positive rate. A false negative would be the test comes back negative. Oh, you don't have the disease. But that's false. You do. So a false negative is a negative verdict that's incorrect. Now the thing about it is these two conditional probabilities do not sum to 1, do not need to sum to 1, are not properly understood as summing to 1. Here we see they sum to something slightly less than 1, but the sums can be further off than this. It's just kind of an accident that their sum comes near 1. There's no real need for that actually. They can vary independently. There are some things that need to sum to 1. Move back up to the sensitivity line there. The probability that you'll test positive for breast cancer, given that you have breast cancer, and the probability that you'll test negative for breast cancer, given that you have breast cancer, that should sum to 1. So what I had there is I had two conditional probabilities with the same thing after the bar, has breast cancer. And then to the left of the bar, I had two different things that were mutually exclusive and jointly exhaustive. Test positive or test negative for breast cancer, given that you have breast cancer. That should be 100%. And something similar applies to the false positive rate. The thing about it is people in the medical field across the nation speak too loosely about the reliability or accuracy of these medical tests. So, for example, some people will simply say, if a test has a sensitivity rate of 0.9, they'll simply say, oh, it's accurate 90% of the time. Well, it's not quite accurate to say that that's what accuracy amounts to for the following reason. There are ways that we can raise our sensitivity rate. So we have a really high sensitivity rate, which might make it seem like, oh, we have a high accuracy rate. But we wouldn't, in fact, have a high accuracy rate. So consider the following situation. Suppose I have a test that says for any woman of any kind ever, she has breast cancer. Whether she does or not, my test is going to say, for everyone ever, she's got it. That doesn't sound like a very accurate test. But if you ask, what is the sensitivity rate for that test? The sensitivity rate is 100%. And let's think about why that's the case. The sensitivity rate is, what's the probability that the test will say, positive, you've got it, if you have it? Well, on my test, what's that probability value? 1. My test will say, if you have breast cancer, my test will say 100% of the time, you've got it. So it's got a sensitivity rate of 100%. But of course, it's horribly inaccurate. If you don't have breast cancer, my test will say 100% of the time, you don't have it. This shows that the sensitivity rate is not the accuracy rate. In the present example, I raised my sensitivity rate by also raising my false positive rate. Every woman who has breast cancer, every woman who has breast cancer will show up as a positive test, but every woman who doesn't have it will test positive. So I raised my sensitivity rate, but I inappropriately, dangerously, whatever, recklessly raised my false positive rate. Every woman that doesn't have it will be told they do have it. 100% false positive rate. Well, that's no good, obviously. So a lot of people don't really, as extreme as that example sounded, there's actually, the idea behind it is something very simple and that everyone needs to understand, and that is, when you raise the sensitivity of a test, you're sort of, you can make a test kind of operate on a hair trigger, as we say, meaning the slightest little hint of any lumpy thing in your breast on the mammography test may trigger, oh yeah, you got it. I mean, you don't want to make even a slightest sort of thing that might show up, trigger upon a positive test. But in some sense of sensitivity, that's part of what sensitivity is about. Okay, so the idea is in medical tests, we want sensitivity, but we want sensitivity without high false positive rates, and it's just an empirical fact that those things are often hard to come by. Okay, so if you ask a doctor, you give a doctor this kind of information that I have here on this slide, these 3 bits of information, and you ask a doctor how reliable, how accurate the test is, they're probably going to say 90%. That's not quite right. But then, more disturbingly, you ask them this question, and they very often, doctors, nurses, will give incorrect answers to this. So Kahneman and Tversky were the first people to ask questions of just this type to professionals, physicians, and noting the ways that they're horribly inaccurate. Kahneman and Tversky found that most humans are sort of bad at these kinds of problems, but it's especially worrying when the tests in question are medical tests and your life and likelihood and potential chemotherapy, potential breast cancer surgery, potential prostate surgery, etc. is at hand. It's more worrying when the people handling those kinds of life-changing, life-altering outcomes are unable to get the answer right. So let's consider this question. What is the probability that someone has breast cancer given that they test positive? The most common answer to that is 90%, and that's a mistake. What the people do here is they take that second statement up there on my slide, the one concerning sensitivity, and they look at the inverse probability. But probabilities cannot be switched around like that. So the sensitivity statement has the probability of a positive test given breast cancer. The fourth statement here on our slide has the probability of breast cancer given testing positive. You can't just switch around those two things and expect the numeric value to be the same. And that's what a lot of people do. So it is not at all 90% likely that you have breast cancer. So think about how I've contrasted Bayes' rule with straight rule thinking. Bayes' rule says you take your present evidence and you put it together in a particular way with background information. So that suggests that we need to take present information about the fact that you have had a positive test and put it together with background information of the right kind. Background information about, for one thing, the prevalence of breast cancer within the overall adult female population, and put it together with background information about some of these conditional probabilities that we see here. So let's look at Bayes' theorem, and let's plug in particular values. So the hypothesis here is you've got breast cancer. The present evidence is you have tested positive. Okay, well, we have the simple formulation of Bayes' theorem here. Now we need to plug in some values. So the probability of H is just the prevalence, the background prevalence of breast cancer. So let's plug that in, 0.001. Now in the numerator of Bayes' theorem, we also have a likelihood value. What's the probability that you would in fact find that evidence, that test value, if you actually had the disease in question? So this likelihood value is equivalent to our sensitivity rate. So in our numerator, probability of H, that's going to be the prevalence, background rate, base rate, prevalence of breast cancer. Our likelihood value, probability of a positive test given breast cancer, is going to be 0.9. Now we've got to answer the numerator. Now you'll notice the way that I've, because of the math that's involved here on your screen, I have had to use the more complicated version of calculating the denominator. So the probability of E is the probability of having a positive test, period. So not only do people sort of fail to take into account the background prevalence of the disease, they also fail to take into account what goes into the calculation of the probability of E here, the probability of a positive test. And importantly, there are two different ways to get a positive test. One way to get a positive test is you've got the disease and the test tells you you've got it. Okay? But another way to get a positive test is to have a false positive. You don't have the disease, but you test positive anyway. So there are two ways of getting a positive test. That's what E is. And that's what we have represented here in this calculation. So look at the numbers there in the denominator. On the denominator, we have initially 0.001 times 0.9. This represents one way of getting a positive test. 0.001, background rate of breast cancer, times 0.9, the probability that you'll test positive given that you actually have it. Okay, so the product of these numbers represents the way of getting a positive test where you have it and the test detects it. But then the other product, 0.999 times 0.09, represents the other way of testing positive. This is where you test positive, but you don't actually have it. So the 0.999 is the 999 women out of 1,000 that don't have breast cancer, right? We just took the prevalence of breast cancer and we subtracted it from 1 to get this value. So out of all these women that don't actually have breast cancer, if all of them were to get a test, 9% of them are going to get a false positive rate, and it's going to be a cause of a lot of concern. They will have tested positive for something very serious when they don't in fact have the disease in question at all. So when you multiply through, look at what we get for our posterior probability value, 0.0099. So that's about a 1% chance. And remember what this is an answer to. This is an answer to the question, what is the probability that you have breast cancer given that you tested positive? Only about 1%. So your doctor will tell you, oh, this test is 90% reliable, and you have tested positive on a 90% reliable test. Well, that sounds like you've really got it. But when you factor in false positives, you factor in prevalence, and the fact that it's a somewhat rare prevalence, the real outcome is how worried should you be when you you test positive for cancer? How worried should you be? Well, just 0.01%. There's only a 1% chance that you've actually got breast cancer, even though you tested positive. And something like this is actually true for the prostate-specific antigen test for prostate cancer in men. So lots and lots of people's lives have been ruined by a failure of healthcare professionals to understand the facts represented on the screen. The prevalence of prostate cancer is quite small. The prevalence of AIDS is quite small. So actually a reason why universal AIDS testing is not mandated, and in fact states and healthcare organizations take specific steps to make sure that not everyone is screened for AIDS, is because of the false positive rate. Again, AIDS is something that has a small fractional prevalence within the population. And when you take something like that and you calculate through and take into account all the false positives, you'll have a ton of people who will test positive for AIDS that do not have it. I mean, thousands and thousands of people will test positive for AIDS, won't have the disease. In the early days of widespread testing and lack of understanding about this, there were quite a few prominent news stories of people committing suicide after testing positive for AIDS. And of course, as soon as your insurance company hears about a positive test, you'll be kicked off the insurance, even if in fact it's quite unlikely that you actually have it. So current best practices for AIDS test indicate that you should only get screened for AIDS if you actually have something in your lifestyle which causes some concern. So you use dirty needles for drug use, unprotected sex, promiscuous something, blood transfusions of if you have, I don't know if just having a ton of blood transfusions is enough, but something that makes it likely that you might actually have something to worry about. Then we test for AIDS. But it's all because of these kinds of results. Let's contrast the last case with a case where the prevalence of a disease is somewhat higher, here at 0.4. I intentionally chose 0.4 because the prevalence doesn't have to be up around 0.9, 0.8 super prevalent. Just as long as it's not very unlikely, we fail to get some of the paradoxical results that we found when the disease is actually quite likely. When the disease is actually quite unlikely. So suppose we have a disease whose prevalence is 0.4, but we leave some of the other features the same, like the sensitivity of the test for this disease is the same, the probability that you'll test positive given that you have the disease, well, that's 0.9, and the false positive rate is the same. The probability that you'll test positive, given that you don't actually have the disease, is 0.09. So now when we ask the same kind of question, what's the probability that you actually have this disease, given that you've tested positive? We get a very different story. We multiply through in the same way. You can look more carefully at this slide later, but we can just, I think, skip straight to the bottom line number. And that is, if you have this 90% sensitive test that you took, and it tells you that you have the disease, and the disease is not a rare one, there's an 87% chance you actually have the disease. Okay, so this is more in line with what we would expect when we hear that a test for a disease has a sensitivity rate which looks a whole lot like accuracy rate, is 90%. When we hear that this test has this kind of sensitivity rate and then it tells you you've got the thing, intuitively we expect the probability to be high that we actually have it. And that's actually right. That turns out right as long as we're not dealing with a rare disease. It's just that when we're dealing with a rare disease, the number of false positives goes up, the prevalence is quite small, and when you multiply through by all that, you get this paradoxical result. So in cases like this, Kahneman and Tversky's favorite label for the kind of mistake where you think you're far more likely to have the disease than you really do. Sometimes they call this committing the base rate fallacy, or just base rate neglect. The base rate is the prevalence of the disease, and so neglecting to take into account the base rate in your calculations is what they call committing the base rate fallacy or base rate neglect. And I think sometimes they're too harsh in their judgments that they make of people, because to say that someone has committed a fallacy, I think primarily means that they should have known better. And I mean, if you think about what I've taken you through with Bayes' theorem, this kind of stuff is just never taught in our schools at the high school, college, any level, unless you specifically take courses in probability statistics and something to do with math, maybe some economics, where you have to deal with these kinds of things. And not everybody has to take those courses, and it's only fairly recent that even healthcare majors are now required to take healthcare statistics. So I think they were too harsh in some of their normative judgments when they would say, "Well, look at all these people committing the base rate fallacy. The implication is look how dumb people are." They don't say that, of course, but that's kind of the message that you get. I like a term that I've seen. I like a term that I've seen more recently, and that's just the false positive paradox. To describe what we've seen, when you have a disease or whatever it is that we're dealing with, usually this comes up in the disease cases, but whatever it is that we're dealing with is very rare. Paradoxical things arise because false positives will tend to outnumber true positives when you're dealing with a very rare disease. So I like this better. False positive paradox, it's not judgy. Base rate fallacy sounds judgy. There's a time to judge. I think it's not the best label. So remember the straight rule. I think too many people do base their belief solely on the result of the medical test. Too many of your doctors will do this. And Bayesian thinking is the right way to go. Bayesian thinking takes into account everything and gives you a better idea of the true probability that you're really interested in, and that's the posterior probability. The probability I've actually got the disease, given that I've tested positive. It's not the likelihood value. It's not these prior probability values. It's a particular posterior probability value you're most interested in. It's Bayes' theorem, the correct use of Bayes' theorem, that gets you to that value you're most interested in. I now want to introduce you to another example that Kahneman and Tversky made famous when thinking about base rate neglect and the false positive paradox. I want to introduce it for a couple of reasons. It's a well-known case. But also the way the case is described is it's described in terms of the overall accuracy of the person making the judgment in question. We saw earlier with our medical test that the sensitivity rate of a test should not be taken to be equivalent to the overall accuracy rate. So I want to show that once you do take in reason from the perspective of an overall accuracy rate, it still gets kind of tricky. So that's one thing. It's tricky to figure out the right answer, and lots of people make wrong answers, or give wrong answers to these questions. But something else about this example that I want to introduce is the visual depiction of the data. Because there's a variety of people, like Gerd Gigerenzer and others, who claim that people are bad at handling the ideas behind Bayes' theorem when the information is presented in terms of decimal fractions, percentages. But when people are able to when they're able to visualize the data and to think in terms of a certain kind of frequency, that they do much better. So there's how the data is presented, Gigerenzer suggests, can make people far better at realizing what the correct verdict is in these false positive cases and in many other cases. Okay, so let's look at this case. The case is, in the Vietnam War, there are Cambodian and North Vietnamese jets operating in some area. Keep in mind that Kahneman and Tversky, when they did their groundbreaking work on heuristics and biases, were working in the early 70s. So suppose that, out of all the jets operating in this area, suppose that 80% of them are North Vietnamese and 20% are Cambodian. So you'll recognize these as base rates, background frequencies. So let's suppose that there is a particular U.S. pilot. He's flying his own jet, and he's got to identify which jets are which. Because we're not supposed to be at war with Cambodia or something like that. Suppose that he has identified some jet as Cambodian, and suppose that the pilot's identifications are correct 90% of the time. Now this is different than a sensitivity rate. As we'll see, a sensitivity rate is one conditional probability. As will this overall accuracy rate pertains to twice as many kinds of things as the sensitivity rate applies to. Now, the key question we're going to be asking ourselves as we work through this example is, what's the probability that that jet really is Cambodian, given that the pilot identified it as Cambodian? Now, it's tempting to think that the answer is 90%. The guy is right 90% of the time, and all of his identifications, he identified it as Cambodian, so 90%. It turns out that the answer is a bit more complicated than that, and that's because the prevalence of Cambodian jets is smaller. It's on the minority side. So let's work. So here's a set of jets, 100 jets. And let's think about how to divide them up visually. Well, the background rates you were given said, well, 80% of the jets are North Vietnamese. So I've drawn a box around 80 of the 100. 20% of them are Cambodian, so I've drawn a box around the remaining 20. Now, our pilot is correct in his identifications 90% of the time. That means out of, suppose he sees 80, these 80 North Vietnamese jets, well, 72 of them, that's 90%, he's going to correctly identify as North Vietnamese. But 88 of them, that's 10%, he's going to incorrectly identify as Cambodian. Now let's apply his accuracy rate to the other side. There's 20 jets that he will see, let's suppose, that are Cambodian. 90% of the time, he will get things right. Well, 90% of 20 is 18. So 18 of the Cambodian jets will be correctly identified as Cambodian, but 10% will be incorrectly identified as North Vietnamese. Okay? Then what we have to do is we have to think about what is the total number of jets that he actually identified as Cambodian. And there we have to add together two things. First of all, those are the ones that those are the Cambodian jets that were correctly identified as Cambodian jets. And then there were the North Vietnamese jets that were incorrectly identified as Cambodian jets. So if you look at the total that he identified as Cambodian, well, we take 8 from the left, that's 8 in the red. That's the 8 North Vietnamese jets that were incorrectly identified as Cambodian. And then from the right, we take the 18 out of 20 that don't appear in the small red box that were correctly identified. Okay, so 26 jets total out of 100 have been identified as Cambodian. Not all correctly, but that's the total that's identified as Cambodian. And we would have to do the same thing as well if we wanted to think about the total number of North Vietnamese, total number of jets that were identified, correctly or incorrectly, as North Vietnamese. Okay. So, when we look at the percentage, so the probability that a jet really is Cambodian, given that it was identified as Cambodian, we have to have taken into account how many were identified as Cambodian first. That's what's in the reference class. That's what's to the right of the bar. So how many were identified as Cambodian? 26. Total identified as Cambodian. Now, out of those 26, how many were correctly identified as Cambodian? That will tell you the frequency of actual Cambodian jets within the set of identified as Cambodian jets. So that's going to be 18 out of 26. Right? So remember, we added up to get our 26 of total that were ID'd as Cambodian. We had our 8 incorrect identifications as Cambodian, plus our 18 that were correctly identified. So 18 out of 26 is about 69.69. Okay, so this means that the central answer to our question is 69%. Our central question was, how likely is a jet to be Cambodian given that this guy identified it as Cambodian? And given that he's 90% accurate in all of his identifications. The correct answer is not 90%. It's only 69%. And the thing that pulled the percentage down from 90% to 69 is it has to do with the less frequent prevalence of Cambodian jets within the overall whole. The smaller proportion of Cambodian jets is what leads to this. It leads to the false. The number of false positives being kind of high in relation to correct identifications. So this is another case where you have a small prevalence affecting the value of some posterior probabilities in some surprising ways. Initially, we were dealing with very small prevalence values like 0.001 as the prevalence for breast cancer within American adult women. Here we have a prevalence of 0.2, which is not crazy small, but somewhat small. But as I said, I wanted to introduce this example because it's a well-known example. It's made famous by Kahneman and Tversky in some of the literature. Also because it uses the overall accuracy rate of the guy. But again, you have to take account of the, as you saw how we worked through the example, we had to apply his overall accuracy rate separately. First to the Vietnamese side, we applied it to the 80 Vietnamese jet, and we determined how many of those would he identify correctly versus incorrectly. And then we had to apply it separately to the Cambodian jet side, and then do some kind of sum and take a fraction. But also a key feature of this is that we have things laid out visually. So Gerd Gigerins thinks that if you present things to people in terms of like the initial presentation of the information is not in terms of percentages. If the initial presentation is in terms of this, which is called an icon array, he's done a variety of tests to show that people are going to get the right verdict all the time. So initially in this problem, I presented the information as percentages, like what percentage of the time does the pilot make a correct identification? What percentage of the time is a jet a Vietnamese jet? And then I had to translate those percentages into pictures and subsets of icons. Well, Gerd Gigerenzer has done a variety of studies showing that if you just do the initial presentation to people in terms of pictures, icons, you don't expect them to go through this somewhat complicated process of translating percentages into icons or just trying to do math just with percentages. If you give them icons and ask them to do tasks on icons, their performance goes way up. Way up. People are much better naturally at thinking in these terms. You have icons, each representing one person or 1,000 women or something, and then you sort of color code or draw boxes around subsets of these icons. People are very good at this kind of thing. So in this kind of fashion, I don't give any sort of particular stats from some of Gigerenzer's studies, but he wants to suggest that the pessimistic conclusions of Kahneman and Tversky about our ability to reason in the proper Bayesian fashion may be more a problem with our ability to handle percentages, decimals, fractions. Like, we can maybe do okay Bayesian reasoning if we're given icons. One icon to represent one data point. Here's another slide I'll show you where Gigerenzer has worked with some healthcare statistics people to sort of try to include icon arrays in doctors' offices. So here's one. Gerd Gigerenzer works with the Harding Center for Risk Literacy to try to come up with better ways to educate people about the risk that they actually face in their lives. Part of this is just giving them information that they don't have. But the unique contribution that Gigerenzer is trying to make is it concerns the presentation of the information. Now, this is a particular poster that's available from the Harding Center for Risk Literacy, and they have a variety of posters like this. This is one for breast cancer. They have some for prostate cancer and many other things as well. And you have a bunch of dots, 1,000 dots on the left and 1,000 dots on the right. And the dots are color-coded or otherwise labeled. And the idea is if you can just present information, you've all seen posters, I assume, hanging on doctors' offices' walls. The thought is if you can, healthcare professionals can better communicate and expect their patients to better understand what in the world is going on if icon arrays of this sort are given to them. So there's no percentages here. There's no decimals. There's just dots and subsets of dots. And this shows out of 1,000 women. The red will show women who died from all types of cancer. And then red with a B in the middle shows women who died from breast cancer. Now this particular icon array is trying to say something negative about mammography screening. So in addition to just trying to make people more risk literate, Gerd Gigerenzer is also campaigning against the regular use of mammograms, the regular use of prostate cancer screenings, because of all the false positives that result, and because of some data that he has showing that early detection actually doesn't actually prolong your life. So it turns out that early detection of prostate cancer, if you look at all the stats, compare early detection and late detection, early detection does not make guys live any longer. Early detection of breast cancer does not make women live any longer. You can read about this in his book called Risk Savvy, and some of the later chapters like chapter 9, 10. It's a striking and surprising result because we all hear and are told that early detection is the key to cure. That's actually false. That's actually not borne out by the actual health statistics. In the case of men, early detection leads to a lot of unnecessary roto-rooter surgery, which makes men impotent and incontinent for the last years of their life without prolonging their lives by a single month. So some of this bad news about cancer screening is represented on the right. Well, actually, so on the left and the right are two sets of 1,000 dots. Okay, the 1,000 dots on the left, as you can see, are 1,000 women who did not participate in breast cancer screening, and how many of them died from all types of cancer. 21 out of 1,000 women didn't get women over the age of 50 didn't do any mammography screening whatsoever. Well, for 10 years or more. I'm not completely sure how to interpret the 10 years or more. They did, in the time in question, they didn't do any screening. Over on the right, we see 1,000 women, all of whom participated in mammography screening. How many of them died from cancer? The exact same number. And by the way, these stats aren't just limited to 1,000 women and 1,000 women. I mean, there's tens and tens and tens of thousands of women who data from tens and tens of thousands of women that stand behind this graph. It's just for graph purposes. They just show the prevalence out of 1,000. That's all. So participating in screening does not make you die any less. But now look at the blue dots. There's this sort of lighter blue. These are women who learned after a biopsy that their diagnosis was a false positive. That's 100 bright blue dots. 1/10 of women, of the women on the right who participated in screening, were falsely given a reason to panic. They did not, in fact, have breast cancer. 100 out of 1,000 women were told, you have tested positive for breast cancer. Of those women, look at the bright blue, darker blue dots. We have 5 out of 1,000 women are diagnosed and treated for breast cancer unnecessarily. So these are 5 women who have mastectomies or something like that, some kind of surgery to remove a lump that's not actually a cancer. It's just you're a little lump. You got a lump. That's it. You got a dense fat deposit or something. I don't know. On this particular chart, by the way, it's not completely clear to me why this dark blue is not in fact a subset of the light blue. It seems like the dark blue women are women who also experienced. No, I guess that makes sense. I guess it's then 105 women who have a false positive altogether. That's the total false positive rate. 105 out of 1,000. And I suppose, so then I guess the light blue is, of these 105 women who had a false positive, thankfully, after further tests, 100 out of 105 figured out and were told, oh, false positive. Sorry about the week, 10 days of panic that we sent you through. And I guess the 5 are the ones who just went ahead. In any case, I had looked around on the Harding Center for Risk Literacy's website and some of Gigerenger's own slides for other sorts of icon arrays that weren't quite so pessimistic and weren't so much trying to grind a particular axe concerning the sort of lack of efficacy of early screening. But the general idea is, whatever kind of information you're going to present to people, Gigerenzer has done a lot of studies showing that when you present people a bunch of dots and you allow them to visualize subsets of dots and subsets of subsets, they're just better able at handling this kind of information. And they're able to come to the conclusion that Bayes' theorem says you should come to. It's not that we're incapable of Bayesian reasoning. It's just that it seems to be, according to Gigerenger's study, harder to reason like a good Bayesian, or in accord with Bayes' theorem, I should say. when we're dealing with percentages and fractions. But visually, we seem to be more innately equipped, better innately equipped to deal with those kinds of things. One other thing that researchers like Kahneman and Tversky and others like Gigerenzer have found is that not only are there differences in how accurate we are when reasoning about frequencies, when the data is presented in terms of percentages or when it's presented in terms of, well, out of every 1,000 people, 10 are like this, and then out of the remaining 10, 4 are like this. Not only are there differences in accuracy, but there's also differences in vividness. So here's an example which I believe is due to Kahneman and Tversky, where they presented some information to psychiatrists. Some psychiatrists presented information in this form. Psychiatric patients, similar to Mr. Jones, are estimated to have a 10% probability of committing an act of violence during the first several months after they are released from the psychiatric institution. Now, the same information was presented in another way to a different set of doctors. Out of every 100 patients, similar to Mr. Jones, 10 are estimated to commit an act of violence during the first several months after discharge. Now, of those psychiatrists who were presented with the first description, 21% of them denied discharge to the psychiatric patients in question. But when a different set of psychiatrists were presented with the second way of describing the very same information, 41% of them denied discharge. The explanation is supposed to be something to do with vividness. How vividly or how easy is it to imagine 10 people committing an act of violence versus 10% of a certain kind of people committing an act of violence? And Kahneman and Tversky, and using a variety of pieces of data, think that the frequency formulations, those are the ones at the bottom, 10 out of every 100, elicit more vividness. It's more concrete. There's 100 patients. There are 10 people. There's a kind of concreteness to saying there are 10 people who are going to commit an act of violence. Whereas a percentage is very abstract. I mean, the first one says, well, 10% commit an act of violence. I mean, this feels less concrete. And in any case, it made the patients described with the second description seem more dangerous. So, however more accurate we may be on Bayesian kinds of tasks with frequency formulations, we need to ask some very hard and important questions about vividness here. Like, we don't want sort of accidental vividness, like accidental increases in vividness to sort of sway people who are making decisions that concern fundamental facts about the livelihood of others. We don't want little irrelevant things. So it's not clear. I don't know what the answer is as to which of these groups of psychiatrists made the better judgment. Was 21% or 41% discharge denial the more accurate? I don't know who's making the more accurate judgments. But whichever way we go, we need to be. There's a huge difference in percentage of discharge cases allowed versus not allowed. Twice as many people were denied discharge in one case rather than the other, over what seems to be a fairly small reformulation, reframing of the very same information. We don't want people's lives to depend upon little features of reframing. So there's some important social political questions to ask about this as well. So this concludes our discussion of Bayes' theorem. We've seen how the theorem can be used to solve certain puzzles. If you think about the steroid case, we have a weightlifter, randomly chosen athlete, who tested positive for steroids. We were able to come to a conclusion about how likely he was to be from one team rather than another, and sort of state fairly precisely how likely he is to come from one team rather than another. And when we put together this information about this steroid test, together with some background information, you can easily imagine how that kind of thinking that we engaged in there could be used to solve certain crimes. You know the background rates for certain kinds of things, and you're presented with a piece of information, and you can Bayes' theorem can tell you how to put those bits of information together to determine, well, how likely is it that the person committing the crime was this person, or even how likely it was that a crime was committed. A friend of mine, a statistician who recently left UB to go to Purdue, has come up with an algorithm which relies upon Bayesian ideas to determine when radio stations in America have made inappropriate deals with record companies, because he looks at the frequency of how often you should expect a song to be played just given certain factors, and then, well, how often would you expect those particular radio stations to play those same songs if there's an under-the-table deal that, according to American law, is not allowed. And so Bayes' theorem has been put to a lot of crime-solving kinds of purposes. I gave you a brief taste of how it functions in design arguments, one perspective on epistemology, and some very practically relevant ways that it functions in medical tests.